Section 3.2, Population Measures of Dispersion. In Section 3.1, we just finished looking at the mean and the median and the mode as a way to measure where the center of the data set is. In this section, we're going to start looking at the dispersion, or how spread out a data set is. So we're going to start off looking at two data sets. Data set 1 has the numbers 70, 77, 80, 86, and 92. And data set 2 is 59, 70, 80, 97, and 99. And just to give context to this, we're going to consider those to be test scores. So let's look at this chart where we're going to try and do our old measures of center, the mean, median, and mode. And I want to show you why that's kind of not enough for this data set, or these two data sets. So we'll start off with the mean. So I'll do some scratch work. Actually, it's pretty short. We'll just go ahead and do that on the calculator real quick. For data set 1, we'll add up those numbers. We get 405, and then there's 5 numbers, so we'll divide that by 5 and we get 81. So I would say for data set 1 we're getting a mean of 81. And I'm using the mu that we learned in the last section for the population mean, which is a little odd here, but it means I'm basically considering this to be, this class only has 5 students in it, so we have everybody. And then we're going to look at the other class and do the same thing. So we add up those numbers, which are definitely different numbers, but you'll see add up to 405 just like they did in data set 1. So when we divide by 5 to get our average or our mean, we still end up with 81. So we have a mean of 81 in both data sets, so both of those measures of center are coming out the same. And yet when you look at this data set, I think you would agree that the two are definitely different. So what about if you look at the median? Well, this one's a little easier to do because the data sets are already in order. There's only 5 pieces of data, so the middle number in both data sets would be the 80s. So the median for data set 1 would be 80, and the median for data set 2 would also be 80. And the mode's also fast. It's not very interesting, but it's fast. There is no repeats in either data set, and that's what we're looking for the mode. So for both of these data sets, I would say that there is no mode. So if we were trying to compare these two data sets just by looking at the measures of center, then it looks like we would conclude that these data sets are not different at all. And yet you look at the data sets, they definitely are different. If you thought of them as test scores, everybody in class 1 passed that test, but there was somebody in class 2 that got a 59 and failed that test. So they're definitely different. There's 2 A's in data set 2, but only 1 in data set 1. So they're different, but they're not different in mean, median, or mode. They're not different in measures of center. So if we want to see the difference start to show up in our calculations, we need to start calculating measures of dispersion. So the first one that we can do is nice and simple. It's called the range. And we use a capital R for that. And the range is just the largest value minus the smallest value. So let's do that on the side over here. The range for data set 1 would be the largest value, 92, minus the smallest one of 70. So it looks like our range for data set 1 would be 22. And then if we did the same thing for data set 2, we take the largest value of 99 and subtract the smallest value of 59, and we get the range for that data set is 40. So now we finally have something with the range that's showing us that these data sets aren't the same, and it's saying that they're spread out more, that the distance from the far left to the far right, or from the smallest to the largest, is about twice as big with data set 2. The drawback of the range is the same as what's good about it. What's nice about it is it's fast and easy because it only uses 2 points. The drawback is that it does not use all of the data, and if you're really trying to decide which data set is more spread out, just looking at 2 values might not be enough. Let me just show you a quick illustration of that. Suppose we had 2 data sets, a data set 1 and a data set 2. Doesn't matter too much, I guess I'll do 1 up top and 2 on the bottom. And just suppose these were numbered with the same scale, and that data set 1 kind of looked like this, and data set 2 something like this with a value over here. So which one of these kind of feels more spread out? To me, it seems like data set 1 is more spread out. None of the data is really close to each other. There's no real clusters anywhere. And data set 2 seems to be the one that's less spread out with almost everything piled in one spot. It just happens to have one value kind of off on its own over here. But if you were to calculate the range, the distance from this largest one to the smallest over here is bigger than over here on data set 1. And so I think that just using those two values, we're missing what's going on in the middle, and this cluster right here, we don't notice that. So if we want to start getting a more overall sense of how spread out a data set is, we can't use the range. The range is fine to get a quick idea, but if you really want to dig deeper, you're going to want to look at something like the population standard deviation. So the deviation from the mean is defined to be the directed distance from the mean. You take the difference or subtraction of every data value x minus the mean, and that gives you how far away they are. Sometimes this will come out negative, sometimes positive, depending on whether our original data was on the left or the right, and that's why it's referred to as a directed distance. And we'll see that come up as we look through this data set. So I'm just going to go ahead and walk you through how to build this, and then we'll write the formulas down afterwards. If you're trying to find this thing called the population standard deviation, then what you want to do is start out finding the deviation for all of your x values. We're working with data set 1 here, and for both these data sets we had a mean of 81. So when we go to do our deviations, we're just taking each x value and subtracting that 81. So this first line, what I would be doing is the x, which is 70, minus the mean, which is 81, and I'd get negative 11 there, and that would go in this first spot. So I don't want to show all that work in the table, it gets a little messy, but there's the first one. So that gave us this number, and then we keep going like that. So 77 minus 81, I'll show one more over here on the side. We get negative 4, so that's this deviation. And then just keep going, I'll do the rest in my head. So 80 minus 81 would be negative 1. 86 minus 81 would be 5. And then the last one, I guess I'll write that down too. You have 92 minus 81, and that would be 11. So we see a little bit of this directed distance idea coming up because 70 is 11 units to the left of the mean, and so we're getting a deviation of negative 11, whereas 92 is 11 units to the right of the mean, and that's coming out as positive. So whenever your x values to the left, you get a negative deviation. Whenever your x values are to the right, you get a positive. So this thing is called the standard deviation that we're trying to find. So here's our deviations. And so if you thought, well, what do they mean by standard? Maybe they mean typical. Maybe they mean average. And if you thought they meant average deviation, then you'd probably want to add these up and divide by 5. So if we were to go ahead and do that and start adding these up, we get negative 11, minus 1, and a negative 1. That's negative 16. And then we have 5 plus 11. That's a positive 16. So if we added all that up, we would get a 0. And it turns out that's not a coincidence that we're getting 0 here. That happens for every data set. One of the things we mentioned in section 3.1 is that the average is a balancing point for the data set, and it achieves that balance by balancing the total distances on the left right here with the total distances on the right. So this is going to happen for every single data set, and if all data sets do the same thing here, then we're not going to be able to see differences in spread if we are adding these up and having the negatives and positives cancel out. So there's a couple things that we could do. Our goal here is to get rid of the negatives before we add them up. One way to do that would be to just get rid of the negatives, but it turns out that mathematically it turns out to be a little bit better for the calculations if we square to get rid of those negatives. So if we take that first deviation, negative 11, and we square that, we would get 121, and that would be my first entry here in the x minus mu squared column, and then I would keep doing that. So the next deviation, negative 4, I would square that and get 16. Negative 1 squared would be 1. 5 squared would be 25, and then finally I square this last deviation of 11, and just like the negative 11, when I square it, the negative doesn't matter anymore, and I get 121. So now all of those are positive, and I want to know what the total is. So I'll add those up real quick on the calculator. So 121 plus 16 plus 1 plus 25 plus 121, and we get 284 for our total. So 284. So that's the sum of those deviations, some of the squared deviations actually. And now we could go back to what we were starting off saying we were trying to do, get a standard deviation or maybe like an average deviation. Well, we've just added 5 numbers together, so it might seem reasonable to take that 284, since that came from adding 5 numbers, to then go ahead and divide it by 5. And if we take our last answer, 284, divide that by 5, we get 56.8. And I suppose you could say this was the average of our squared deviations. But when I think of standard deviation, I think of maybe typical deviation or typical distance away from the mean. And if we look at how far away from the mean these numbers were, they were 11 away, 4 away, 1 away, 5 away, 11 away. None of them were anything close to 56.8 away. So this answer is coming out way too big. And why is that? It's because of the squaring. The squaring did a good thing for us. It got rid of the negatives, but it did a bad thing as well. It made these numbers all a lot bigger. So what we're going to do to get rid of this kind of growth we got is do the opposite of that squaring, and we're going to end this process by taking a square root. So we're going to take the square root of that 56.8. This is going to be our population standard deviation. The symbol for that is the lowercase Greek letter sigma, so I'll put that in there. And it's going to be the square root of 56.8, which I'm sure will be messy, so I'll put an approximately equal on that, and let's see how that turns out. We have the square root of 56.8, or our 56.8 sitting there. Now we want the square root of that. And the square root of 56.8, I'm going to round that to 7.536, and I'll write one more digit, and it's a 5, but it's followed by a 7, so I'll write a 6 for that. And then I just want to kind of show you that does make sense as a typical distance away from the mean. Now instead of having a number that's way bigger than all the distances, at about 7.5 we have 2 values, 70 and 92, that were further away from the mean than that, and then 3 values that were closer to the mean than that. And if we're trying to get some sort of typical distance, we'd like to see it have that trait, that there's some numbers that are further away from the mean than that, and there's other ones that are closer. So that's your first look at calculating population standard deviation. I'll go ahead and show you the formula here as well. So when you're doing the population standard deviation, you use the lowercase Greek letter sigma to represent that, and you take the square root of the sum of the squares of your deviations divided by the size of your population. So that looks pretty messy, and the best way to handle this messier formula is to do it in pieces. So we found our mean, and then we subtracted everything, then we squared, we added, we divided, and finally we took the square root. And we'll look at that process again on the next page, so we'll get some more practice with it. And then one other definition is the population variance. That would be the sigma squared is called the variance. It's the same thing, it just doesn't have the square root on it. So if you thought about that in terms of this example, you could say that the variance was 56.8. We don't use the variance much in a intro stat class. We focus more on the standard deviation, but this is also an important term in statistics, so it's at least good to be aware of what that is. Alright, we're continuing on with section 3.2 on the standard deviation, and I just want to make a note here. If it's really the job of the standard deviation to measure how spread out a data set is, then the more variation there is in a data set, you would think the larger its standard deviation would be. And we're going to kind of test that theory out here by looking at the standard deviation for our other data set 2. So if we were to go back and look at the data sets from the previous page again and compare data set 1 to 2, we know from the range that it seems like the distance from one end to the other is smaller for data set 1, so we would kind of tend to think that data set's more spread out. But even when you look in the middle, 70 and 97 are further away from each other than the 77 and 86. So I think we do have more spread in data set 2. So I would expect that when we calculate the standard deviation for data set 2, it's going to come out to be larger than data set 1, because it just looks like that data set's a little bit more spread out to me. So to this question of how do you think the population standard deviation for set 2 compares to set 1, I expect it to be larger. And now we're just going to run through and calculate the standard deviation for data set 2 and kind of confirm my suspicion there, I hope. So let's go ahead and do that process. So you might remember that both data set 1 and 2 had the same mean of 81. So my first number in this chart would be 59 minus 81, and I believe that's negative 22. So I'll go ahead and fill that in. And then continuing on with that kind of calculation, 70 minus 81 would be negative 11. 80 minus 81 would be negative 1. 97 minus 81 would be 16. And our last number, 99 minus 81, that looks like that would be an 18. And we don't really need to add this number up because we're not going to use it, but if we wanted to confirm our work, we could do that. The 16 plus 18 is 34. Negative 22 and negative 11 would be negative 33, and another negative 1 would make it positive 34. Sorry, negative 34 altogether. And we have that positive 34 down here that would cancel that out. So once again, we do see that the sum of the deviations is turning out to be 0, which again isn't really useful for us other than as a check. So we're going to need to go through and start squaring these to see what we get for them. And some of these I know, but some of them I don't. So let's go ahead and take the 22 and square that one. That'd be 484. Also square that 18, that's 324, and I think I can do the rest in my head. So let's see, for negative 22 squared we'd have 484. You might have noticed I didn't put the negative in the calculator. You always get the same answer when you square a number that has the same absolute value, whether they were negative or positive to begin with. The negative 11 squared is 121. Negative 1 squared is 1. 16 squared is 256. And the 18 squared, as we saw in the calculator, is 324. And according to the formula, and I'll write that down, we want to get sigma 2 here. We want the square root of the sum of the squared deviations divided by the number of data values. And I'm just going to extend this down because we want the square root of the whole thing. So I've just found all of the squares of the deviations here, and now I want the sum of that. So I'm just going to do that off to the side here on the calculator real quick. And I get 1186 for that sum. And so I'm going to want to plug that in here. Our sigma, our second sigma for data set 2 would be the square root of 1186, which is the sum of our squared deviations, divided by 5, which is the number of data values we had in this small population. And on the last example I did the division in one step and the square root in another, but typically if you do the division first, you're going to see the variance, and then you would take the square root and you would get the standard deviation. But in this class our focus is on the standard deviation, so I'm just going to do both those steps at once and say that I have the square root of 1186 divided by 5. And I'm going to round that using 5 digits altogether, so 15.401, so 15.401. And I'm going to go ahead and summarize the work that we've done here so far. We had our mean, median, mode from the previous page's work, and then we figured out our standard deviation for data set 1 on the previous page, and that was 7.5366. And now we figured out the standard deviation for data set 2 is 15.401. And we said that, if you look right back up here, we said data set 2 was more spread out, so we expected it to have a larger standard deviation. And now we see that is in fact what's happening. When you look at the two numbers there, you might think that it's a little inconsistent the way I did the rounding, and you would think that, I think, primarily if you were to focus on the number of decimal places, because I used 1, 2, 3, 4 here, but only 3 in this spot. When we do the standard deviation, this is a number that's going to be involved in a lot of multiplications and divisions. And when you're multiplying and dividing by a number, as far as accuracy goes, you're more concerned with how many total digits it has in it rather than just decimal places. And so I focused on that, and I did 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 on this one as well. And that's the minimum that we're going to have for our rounding rule. So the rounding rule for standard deviations is to use at least 5 digits. You might also be familiar with the idea of digits in a different phrasing. If you took a class in science like chemistry or maybe physics, you would have heard these referred to as significant figures, or sig figs, sometimes they call them. So either way of referring to them is fine, but when we do a standard deviation, it's the total digits or significant figures that we want. It's not just about the decimal places. So I'm going to go ahead and show you just 3 quick examples of rounding with significant figures and then make a couple notes about that. Sometimes these can be a little bit tricky, so you might want to just pause the video for a second and try and round each of these 3 to what you would consider to be 5 significant figures, and then see if you get the same answer as I do. So go ahead and pause, try that, and then come back. Alright, so let me go ahead and show you what I did with these. This one's probably the easiest one. We want 5 digits altogether, so the 1, the 4, the 2, the 3, and the 0. So I'm going to write that this is approximately 14.230. Now, one of the things that's interesting about that is if I didn't write the 0, it'd still be the same number, but it would then only be written to 4 significant figures. And I want people to know that I really went out to the 5th one and it just happened to be a 0. If I leave that off, they don't know. Maybe it was 233 and I rounded it down. Maybe it was 228 and I rounded it up. So I want them to see, no, that was really a 0 in that spot. And then this one is kind of one of the most confusing ones, but it turns out that's not going to be a real big problem for us, the confusion. I'll explain that. If I rounded this to 5 digits, I'd have the 2 and the 1, 4, 5. Now there's 4 digits already, so the 5th one is going to be this 3, and that's going to be the last one I would write as a significant figure, and it'll stay 3 because it's followed by a 4. And then I still need placeholders though for everything from there to the decimal, so I'd put 0, 0. And I would consider that number to be 5 significant figures, 1, 2, 3, 4, 5. So when we have zeros at the end of a large number that are serving as placeholders until we get to the decimal place, those do not count in our list of significant figures. You can think of as an example to that, if you listen to the news and they say what the #1 movie at the box office was over the weekend, they'll often say something like the #1 movie brought in $75 million. And I would imagine you don't think like, wow, exactly $75 million. How could that have been right on the nose? We kind of assume they've rounded that. And that's common with big numbers, that people don't trust the zeros as actually being accurate. They just assume that they were rounded off. This isn't a real concern for us because if this was a standard deviation, I would have just gone ahead and written the 49. Instead of 2 zeros, because it says here at least 5 digits. So I feel like if I'm going to write 7 things, I might as well write more accurate 7 things and go 7 digits instead of just 5. So on a big number like this, if you want to leave the original digits here instead of rounding them to zeros, that's totally fine, because the rule is at least 5, so more than that is okay. The thing that's tricky about part C is that the zeros at the beginning of a small number do not count either. And so when I start counting my digits, I wouldn't count any of those as significant. So the 2 is the first one. So the 2, the 3, the 7, and the 6. Now I've got 4 significant figures written down. I need one more, and so that would be the 2, but it's followed by a 9, so I'd round that up to a 3. And again, honestly, if it was a standard deviation and this is the number I got, I probably would have just kept the whole thing, because the rule is use at least 5 digits. And so if I wanted to use 6, that's not a problem. And the more you use, the more accurate it tends to be anyways. So this is the shortest answer you could put. This is the shortest you could put as far as the rounding. But if you want to put more, that would be okay. Just a quick note about this, by the way. If you were to put these in scientific notation, which we definitely don't need to do, but it kind of explains a little bit about what's going on there with what's important and what's not. This number could be expressed in scientific notation as 2.1453 times 10 to the 6th, and you wouldn't need to put those zeros in the scientific notation, and so you can kind of see like, oh, okay, we only need 5 of those. And if you did this one, it would be 2.3763 times 10 to the -3, and again, you see when we went to scientific notation, we didn't need those digits, just 1, 2, 3, 4, 5. So that gives you maybe a little bit of an insight as to why we wouldn't count the zeros at the end of a big number or at the beginning of a small one. But please don't be confused by this. You don't have to change these to scientific notation. This is the way I would leave all 3 of those if it was a standard deviation question. Alright, we're looking at the last page of section 3.2. We're going to look at one more example. We have the lap times for the first 10 attempts at a new track on Project Gotham 3. The times are rounded to the nearest hundredth of a second. And this was just me playing this video game on the Xbox 10 times, keeping track of my times, and now I want to summarize it. So I think it's legitimate to think of this as a population, and we're being asked to find the population standard deviation. Now, even though we're asked right away for the population standard deviation, we still actually have to begin by finding the population mean, because that's part of the formula. You have to do x minus mu all along the way, so you have to have that mu to begin with. So that's where we're going to start, and that means the first thing I want to do is add up these 10 different times for the different times around the track. And I could do that just using the addition key on the calculator, but I want to show you how to do that using the list editor instead. So what I'm going to do is go into my stat menu. So we'll start off pressing the stat key. We want to go into edit. And I have some data there, so I'm going to clear that out before I get started with the new. And the way you want to do that is use your arrow keys to get up there and highlight the list name. And when you do that, you'll see the whole list down here at the bottom. You press clear, which at first doesn't seem to do anything here, but you will notice that the part on the bottom has gone blank. And when I press enter, that will take care of finishing off the clear. So it actually takes 2 keystrokes to clear a list. First of all, you have to highlight the list name, not just be on a number. And then you have to press clear and down arrow, or clear and enter, one of the two. So I'm going to go ahead and enter this data now, and you could follow along on your calculator as well. Alright, so now that I've entered that data into list 1, I want to use the calculator to add it up. And you could exit out of the screen to do that. You can also just move over and use one of the cells of the next column as just kind of like scratch area. So I'm going to go ahead and do that. And I want to use the sum, which is under this list menu, which is above the stat key, and that's in blue. So to get there, I'll hit the second key and then list. And what I want is under this math menu, so I arrowed over to that, and then I want number 5, which is the sum. You could just hit number 5 right away, but I'll arrow down, highlight it, press enter, and right here it's saying, okay, in this first spot of list 2, we're going to get the sum of something. What do you want that to be? And I want it to be of these numbers that are in list 1. So I'm going to slide the calculator up here so you can see, but above the 1 key you have a blue L1, so I'm going to hit the second key and L1. And then you can see here that I'm getting the sum of L1. And I press enter, and that shows me the value there. So at the bottom of that column, I can put that total 795.36. And then what I really want is the mean. So the mean would be that 795.36 divided by 10. And dividing by 10 is just going to move that decimal over, so that would be 79.536 for the mean. So this messy number is what I'm going to subtract from all of these from all of these x values to get all of these deviations. And fortunately, that's already been done for us for a lot of the numbers, but we still have 3 of them left to fill in for ourselves. And so I'll show you how to do that. Let me go ahead and exit out of here and do that on the home screen. So we have 86.49, and then I'm going to subtract the mean, which was 79.536 from that, and that would be my first deviation, 6.954. And then I just want to show you the one before that, or on the next line also, and we want to make sure we get the same number just to make sure we're on the right track. So 83.79 minus 79, whoops, got the comma there, 79.536, and we get 4.254, which is a match with what's there already. And now I want to do these other two that were blank. I'm going to use the second and enter key just to edit that last calculation. I'll change that to 77.05, so negative 2.486 is this one. I think I'm about to lose that top number, so I better write it down. 6.954, and then that most recent one, negative 2.486, and then we still have the one at the very bottom. So second enter to edit that last calculation. I'll change that to 75.07, and I get negative 4.466. Alright, so a couple things at this point. One of them is you might want to add all these together just to make sure that you get a 0. That would verify that no mistakes have happened. I'll show you how to do that quickly on the calculator in a minute. So we'll just go ahead and leave that for now and go ahead and move over to the squaring. And I'm just going to square just this one, and then I'm going to show you a little bit of a shortcut for both finding these sums and then for doing these last two slots as well. So for the 6.954, I can type that in and then just square it, and I get 48. Let's see, I'll put 4 decimals just like these other ones. So 48.3581. And I could do that 2 more times with these other deviations and fill this in and add that up, but I do want to show you a shortcut on the calculator. If we go back into the Stat menu and into the Edit area, one of the things that we can do that's nice about this is once we have data in here, we can highlight our next column L2, press clear, and instead of just pressing enter and getting a new list, we can tell it what we want L2 to be. And we can say, you know what we really want for this column right here is we want all the numbers that were in this list, L1, with the mean subtracted away. So I want to subtract 79.536 from every one of those. And if I do that, if I let L2 be list 1 minus the mean, then it actually does all 10 of those subtractions for me at once. And you can look down and see our 6.954, our 4.254, and so on all the way through. And now if I want to make sure that those numbers are correct, I can come over to this area, go into the list menu, second list, go over to the math option, down to number 5 for sum, and say what's the sum of L2, and I get 0. And that's what's supposed to happen when you're doing an average and getting deviations. The sum of all those deviations should be 0, so that's a nice check for us. Then let me slide this over here. We could do all of these at once. These are the numbers from L2 squared, so I'll highlight L3, hit clear, and now what do I want L3 to be? The numbers that are in L2, but I want to see them squared. So there's our 48.3581 is right there. You might notice you can't see the 1, but when you have a number highlighted, you can look down here and you can see more decimal places on it. So there's the 1 that I had written down. And then there's our 18, our 0.25, the 3.511, and now the next one we actually needed, 6.1802. You know, we could put a couple more decimals, but the ones we were given only had 4, and when you're adding things, it's best if they're consistent in the number of decimal places. There's our 22, 15, 72, 10.15, and then finally we have 19.945. For that last slot. Now, if you were to add all of these together, just take these 4 decimal place numbers and add them up, which I did a little while ago, I got 115.4927. I just want to show you something real quick on the calculator. That was adding these actual numbers, but if I go over here and I use the list math sum way of doing that, and I add the stuff in L3, and I highlight that so I can see more decimals on it, it's actually 4926. It's a 4, so it wouldn't quite round up to a 7. So when you're doing this, I would encourage you actually to use the one on the calculator and have this have a 6. But if you want to add these and have the 7, either way, that last digit's probably not going to affect our standard deviation. This would be the more accurate one because all of these numbers were rounded, and the calculator here is using the versions that aren't rounded. But again, either one is fine. So just don't be concerned if you see a difference in that last decimal place. That's probably just a difference between you adding up these and the person doing the answer key doing it this way. Alright, so for our standard deviation, we want the square root of the sum of the deviations squared divided by the number of data values. So our numerator is this 115.4927, and I'll use that number just because I have it written down, but again, if you want to use the one with the 6 or even the 6.4, that would be fine. And then divide that by the number of data values we had, which was 10. So let's see what sigma would be. I'm going to go ahead and exit out of here. I want to do the square root of 115.4927 divided by 10, and then end the parentheses, so all of that is in the square root, and we get 3.3984, and that would be 1, 2, 3, 4, 5 digits written down, so that's consistent with our rounding rule. So that one was a messier one, and it certainly would have been even messier if they hadn't filled 7 of them in for us already. So when you get to these messier problems, you might want to take advantage of that idea of putting your x's into L1, and then here letting L2 be L1 minus your mean, and then coming over here and letting L3 be equal to L2 squared, and then take advantage of the sum key to just make that whole process, which can be kind of tedious, go a bit faster. Alright, they have a couple follow-up questions for us here, so let's go ahead and take a look at those. The first one, what percentage of the data lies within one standard deviation of the mean? So the standard deviation is 3.3984. If we have any data values that were within that distance of the mean, we want to count them up and then turn it into a percentage. And when you have a chart like this, kind of the fastest way to do it is to look at the deviations themselves. Don't pay attention to the negative signs when you're doing this. The negative just says whether you were on the left or the right. Just look at the absolute value of these, and if the deviation is bigger than this, then it means the actual number was more than this far away from the mean. But if the deviation is smaller, like this 1.226, then it means your actual data value was within one of these standard deviations from the mean. So we're just counting up basically how many of these deviations are smaller than the standard deviation, and again, not paying attention to the sign, but thinking about the absolute value. And so let's see, not the first two, but this one, this one, this one, this one, this one, this one, and 3.1, that's still smaller than 3.39, but not this last one, 4.46 is bigger than the 3.39. So we ended up with 7 values that lie within one standard deviation of the mean, so that would be, as a percentage, we want to go to 7 over 10, which is 0.70, or 70%. So 70% of our data values lie within one standard deviation of the mean. And then what percentage lie within 2 standard deviations of the mean? To do that, what you want to do is the same idea, but you want to compare everything to 2 times the standard deviation. So that would be 2 times 3.3984. And if I do that doubling, I get 6.7968, and then we just want to count up all the deviations that are smaller than 2 standard deviations. So certainly that's going to still include these, but do we pick any other ones up? Yes. This deviation, let's see if I can get that all where you can see it, negative 4.466, or again ignoring the negative, 4.466, that's smaller than this, so now all of a sudden I'd be counting that one. And then how about 4.254, definitely smaller than 6.7, so I will mark that one. And how about 6.954? That one is just a little bit bigger than 2 standard deviations, so that one won't be counted. So I have the 7 I had before, and then I have 2 more that I've picked up. So what percentage of them are within 2 standard deviations of the mean? Well, that was 9 out of the 10 values, which is 0.90 as a decimal, or 90% of them. And I would just make a quick comment there. When I count 9 out of 10, I absolutely was thinking of that by looking at the deviations, but it actually is asking what percentage of the data. So what we're really saying is these 9 pieces of data right here lied within 6.7968 seconds of the average time of 79.536 seconds. And when we talk about lying within a distance, that could be to the left or the right, so they could be faster or slower times as long as they were within about 6.8 seconds of that average. And then one last note, I did this calculator work using the list editor in L1, L2, and L3, and that can be handy doing the homework. If you want to see the steps written down for that, see the appendix pages in the back of the book. Appendix A for a TI calculator like you saw me use here, or Appendix B for a Casio calculator, and that will kind of take you through the step-by-step that I did to make those shortcut ways of filling in our table. Alright, that finishes off section 3.2.